Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the second part for the lecture number 13. My name is Engineer Jaffar Ali and I am instructor for this course. So this is our second part of the lecture number 13. In the previous class we discussed about the steady state error. We started steady state error. We looked at how you can find steady state error using different test inputs. We discussed three of the inputs. One was the step, the second one was ramp function, and the third one was parabolic function. We also find out that these parameters are applied on the stable system. If you have the stable system, you have the characteristic equation. The first thing that you need to find is the stability of the system, and if the system is stable, you can apply this analysis on this steady state error, and you can find the steady state error. Later on, we discussed about the unity feedback system, that how you can calculate the steady state error for unity feedback system using all of the inputs, the step, the ramp, and the parabolic. And the equations we discussed on the equations that are involved in this was also discussed in the previous part. In the last of the second previous class, we also did two of the numericals as well. One was with the same parameters, and we also found the values of the different steady state error for different functions. The function for the, you can see that, and the error for the step function, the error for the ramp function, and the error for the parabolic function using the final value theorem. So let's continue our lecture, and into this part of the lecture we will discuss static error, constant, and the system type. So based upon different types of error, different inputs, the errors are basically divided into different constants, and these constants are known as steady state error constants, or you can say static error constants. And these static error constants are the performance basically represented that basically specify the performance of any of the equation. So this for a step input, you know that the step input is the physical interpretation of this was constant position. So this is your constant position, you can see over here. So we replace this thing, this limits g limits s, where limits on g of s where s tends to 0. This is replaced with the constant kp, and this kp is nothing but a position constant. So you can denote this steady state error in terms of, for a step input, in terms of a constant position. You can see that constant for the known as position constant kp. Similarly, if you have a ramp input, you can replace this whole denominator with the kv, and this kv is basically velocity constant. So you can replace this whole thing with kv, and this kv have the same formula. Means if you have to find this kv, you will have to find this thing. So this is just a representation for the static error constants. And for a parabolic constants, you know that this was the denominator over here. So you replace this denominator with a constant known as ka, and this ka is nothing but constant acceleration, or you can say acceleration constant. So if you replace this denominator with the ka, you get e parabola is equal to 1 by this ka. Now based upon these three kp, ka, and kv, actually you are going to now have this numerical for each of the systems shown in the big figure below. Evaluate the static error constants and find the expected error and the standard for the standard step, ramp, and parabolic input. So you have to give these three functions to this one, and to this one, and to this one. So this will be our today's lecture. So the first thing that we have to provide or justify is that the system is stable. So the thing that you have to do it by your own is to find the system stability of these systems, and you know that how you can find the stability of these systems. So first thing, you have to find the characteristic equation, then you have to put the RH criteria, and you have to find the stability of the system. Now if the system is stable, then you are going towards the constants that you have kp, kv, and ka for the first one. So for the first signal, this kp is basically for the first system. Actually this system, this let me highlight it for you. For this system, such kind of system, this is a system, you have to find kp, the position constant. So position constant is basically limit of s tends to 0 for the g of s. So if you put this as it equals to 0, you get this kp turns out to be 5.208. Similarly, if you put find the value of kv, you have to put this value, and it turns out to be the value of s. This kv is actually 0 for the first system, and for the second system, for the value of ka for the same system, first system, a, you can see this is the a, and the acceleration constant turns out to be also 0. So for a step input, you get this E infinity will become 1 divided by 1 plus kp, and kp is basically 5.28, so this will become 6.208, and when you divide 1 by 6.208, you get 0.161. If you apply ramp input, now you see these things are very much easier as compared to the previous ones. So you are just applying you have found out the value of kp, kv and ka. Now you are just putting in the formula. For ramp input, the system stability error will be, the system steady state error will be 1 over kv, and you know that kv is equal to 0, so the error will be infinity. Similarly, for a parabolic input, the system steady state error will be 1 divided by ka, and this ka is nothing but 0, so the values turn out to be infinity as well. So let's take the second system. The first thing you have to find is the stability of the system. So let's say the system is stable, and the second thing that you are going to proceed with is basically to find the values of this kp, kv and this ka. So this kp turns out to be infinity, this kv turns out to be 31.25, using the same methodology that we are discussing in the previous lecture and till now, and the value of ka turns out to be 0. So if you put the values for all of the input, for a step input, this formula will be 1 divided by 1 plus kp, and you see that this kp is equal to infinity, so 1 plus infinity becomes infinity, and anything divided by infinity basically becomes 0. So the steady state error for the first step input for the second system, actually you can see this is the second system, B system, the steady state error turns out to be 0. Similarly, if you apply ramp function over here, the steady state error equation becomes 1 divided by 1 by kv, and this kv is basically 31.25. So if you divide this thing, you get 0.032 error. So the steady state error for ramp input for the second figure will be 0.032. This is the figure. Let me show you. This is the second one is the figure. This is the figure that we are talking about, and you see that if you apply the ramp input, the parabolic input, the formula is to find the steady state error for the parabolic input is equal to 1 divided by ka, and this ka was 0, so anything divided by 0 becomes infinity, so the steady state error becomes infinity for a parabolic input for the second system in the figure. Similarly, you have to find the values of kp, kv and ka for the third system, and it turns out to be that the kp and kv was infinity, and the ka becomes 875 for the third system. And if you put these values of kp, kv and ka in the equations for the steady state error, so for the step input, this things becomes infinity, and anything divided by infinity becomes 0. For the ramp input, 1 divided by infinity becomes 0, and for a parabolic input, 1 divided by ka, and ka was 875. If you divide 1 by 875, you get 1.14 into 10 power minus 3. So this is the error for the parabolic input. So this was your numerical. Now, depending upon these types of error, this types of this standard, this constant static error constants, you can find the type of the system as well. So the values of the static error constants depend upon the form of this GS, especially the number of pure integrations in the forward path. Since steady state errors are dependent upon the number of integrations in the forward path. So you see that if there is an n this is an, there is no n, let's say there is no n, so you can see that if you move this thing, you will have an idea that this is basically a first type of system. This is type of the system. Let me tell you, this is the type of the system. You can see that in all of these numeric, in all of these figures, there is the only difference was the presence of s, actually the presence of s in the denominator. So you see there was no s over here, there was one s over here, and there was 2s over here, s square over here. So this basically represented all of these things. So if we define the system type to be the value of n in the denominator, you see that I have blurred it, let me clear it for you. So depending upon the value of n, you will find the system type. For a system with the n is equal to 0, this will be considered as type 0. For the system, if the value of n is 1 or n is equal to 2, the corresponding system will be type 1 or type 2. So if you see the this thing, by seeing the images of the system, you can see, take the or you can find the type of the system. This is a type 0 system because the s power, there is s power 0 in the denominator. This is s power 1 in the denominator, and this is s power 2 in the denominator. So depending upon the power of s, you can actually put the type. So this is the type 0 system. There are three types: type 0, this is type 1, and this is type 2. Now let's go forward. So you can see that this is a type 1 system. From there you can see that this is S over here, and this is the type 2. Actually this is type 2, and this is type 3. Type 1, type 2, and type 3. So this is type 0. In the type 0 system, you see that the input that in the type 0 system basically will be tested upon the step input. You won't be able to test your type 0 system with the ramp and parabolic input because it will be giving you infinity values. For a type 1 system, you will have to check your values on this ramp input to find the accurate value of the steady state error, because if you apply a parabolic equation, parabolic input to that type 1 function of type 1 system, you will be getting infinity steady state error, and if you apply the step input as a input to your type 1 system, you will be only receiving 0 error. So you won't be able to find the accurate error. So for that you have to apply the ramp input. Similarly, if you apply if you are having a type 2 system, so you have to apply a parabolic input to that type system to find the accurate value of the steady state error. And if you have a type 3 map, basically you can apply any of these because all of these will be showing 0 error. So this is the relationship between the input and the system type. Now we have to find the state. This is another example with the inputs of step, ramp, and parabolic. You have to find the value of the ESS. So you see that the system, the closed loop poles are there are 3 poles actually, because the roots will there's 3 roots basically. You can find the roots of this. Basically this is nothing but s cube plus 12 s square. So this is the third degree polynomial equation. So you have to find the roots, and there will be 3 roots. So the first root is basically on the real axis, and the 2 roots that are involving the imaginary axis as well. So the system is basically stable and of type 2, and 0 steady state error for step and ramp input, and for parabolic input you can find the steady state error. It will turn out to be 12 by 5. You can see that the first thing we found out is the stability of the system as it is, and after that we looked at the type of the system. So this was type 2 basically. You can see that there is 2, so this is was a type 2, and we know that the only input for this type 2 will be the parabolic input. You see that in the previous table I showed you that for the type 2 system you have to apply parabolic input, and all the other inputs will be resulting zero steady state error. So that is why I didn't try to make that effort. I just put it that is equal to 0 for the step input and the ramp input, and just found out the values of the steady state error for the parabolic input. I just mentioned that there will be zero steady state error for both step and ramp input, and parabolic input was given by 1 over Ka. So I have to find the Ka first, and Ka was found out using the formula, and 1 over Ka turns out to be 12 by 5. Now let's talk about the different specifications for this SSE or steady state error. Steady state error constants basically are used to specify the steady state error characteristic of a control system, because you know that different just like overshoot and damping ratio, settling time, peak time, you are able to specify the transient response of a control system. Similarly, by using this Kp, Kv and Ka, you can find the steady state response or steady state errors or for a given control system. So if you have a control system has a specification of kV, let's say 1000, we can draw several conclusions. The system is stable, the system is of type 1, the system input, the ramp input is a test signal, and ES is 1 by kV. You can see that just because it was mentioned that there is a kV of 1000, the constant of that velocity constant was 1000, so you know that the system is stable. The type 1, because you know that this kV is also only for the type 1 system, and for type 1 system the recommended input is the ramp input, and the formula of steady state error is 1 over kV. Just because from the value of this kV we have derived several conclusions. So depending upon the values and the specifications, we can actually draw conclusions, and we can reach to a point which is not specified before. So let's talk about another example. What information is contained in the specification when you say that Kp is equal to 1000? So if you say that Kp is equal to 1000, it means the system is basically stable. This is type 0 system, and since type 0 has a finite Kp, so it should be type 1, and type 2 systems have Kp infinity. So the test input is basically a step function, and since Kp is specified, finally the output, you know that 1 divided by 1 plus Kp. So 1 divided by 1 plus Kp, 1 divided by 1 plus 1000, and the steady state error will turns out to be 0 point something, 00 something, because it is 1 divided by 1000. So let's do this last example of this lecture. Actually, for a given control system, in the figure we have to find the value of K in such a way that there is only 10% of steady state error. So what will be the value of K that the error should be not more than 10%? So the first thing that we need to start is with this checking of the stability. So this, if the system is of type 1, the error stated in the problem must apply to a ramp input, because you know that this is a type 1 system. It is mentioned that this is S over here, so it will be a type 1 function, and we have to apply a ramp input, because only a ramp input will yield a finite error in the type 1 system. So the first thing that we have to find is basically kV. So it was given that the steady state error was 10%. So 10% means 0.1. So from here you can find the value of kV. So from here you can see that this kV is equal to 10, and if you just take the inverse, so you get the value of this kV, and you know that this kV is equal to k plus k multiplied by 5 divided by 678, and from here you can find the value of this k. This k turns out to be 672. So we did the opposite or reverse methodology, or you can say reverse engineering. With the help of this 10%, we actually found out the value of this k, that what should be the value of this k, so that the error would be 10%. So if you put this value of k is equal to 672, you will get, and you find the value of kv, you will get the value of steady state error as 0.1, or you can say 10%. So this was all about this week's lectures. I hope that you have learned quite a lot. I have restricted myself to a few of the topics because this involves a lot of mathematics. So that is why I have not done much numericals. I have already limited to 3 or 4 numericals, or maximum 5 numericals in a class of 30 minutes. So I will continue this. This lecture will be continued in the next week as well, and inshallah by the end of the next week we will be able to complete this chapter as well. So also I will highly recommend if you write down some good questions and practice some good practice some numerical questions or problem questions, or you can also try to solve the skill questions that are mentioned in the book as well, because the more practice you do, the more confusion and missing conceptions will be removed, or you can say cleared. So I wish you all the best. I'll see you in this next in the class actually. Try to watch this video as many time as possible along with the practice. Do the practice, pause the video in between, and do the same numerical along with the video. Thank you very much. I'll see you in the class. Allah Hafiz.